All right, so let's talk about calorimetry. So if you remember, when a hot object comes in contact with a cold object, they transfer heat. And the way we said that was we said Q was equal to the mass times the specific heat times the change in temperature, right? This is sort of the standard equation that we use. And so we would know that Q from the hot object will be the opposite of the Q of the cold object, right? Remember that negative sign just talks about direction of heat flow, right? So the direction of heat flow for the cold object is opposite that of the direction of heat flow for the hot object. And so in calorimetry, right, with that coffee cup calorimeter that we could use, that maybe you used in high school, or we did the simulation in lab, we would say, we talked about mixing two things. In lab, in class, we said, well, let's put a metal object into some water, and then we did a calculation, right? We said for the Q of the metal, we substituted in what? The mass of the metal, specific heat of the metal, and the change in temperature of the metal. And we said that would be the opposite of what? Of the mass of the water times the specific heat of the water times the change in temperature of the water. Okay? And so that's sort of the standard thing we do. We said we know what temperature the metal starts at. We know what temperature the water starts at. And so we could calculate a final temperature. And so maybe as an example, we could say that we had, I don't know, maybe 50 grams of iron. And we could look up the specific heat, or somebody would tell us, and we'd see that it was 0.444 joules per gram degrees C. And maybe we'll heat the metal up pretty hot. Let's heat it up to, I don't know, maybe 120 degrees C. So we'll have the final temperature minus the initial temperature. So that's for the metal. Okay, and for water, let's say we've got maybe 100 milliliters of water, which is close enough to 100 grams of water. Heat capacity of water, 4.184 joules per gram degree C. And let's say the water started at 25 degrees. So we'll have temperature final minus 25 degrees. And so there we have it. So in this case, then, it looks like we've got one equation, right, with one unknown, right? So there's the unknown. We would have to solve for the final temperature. And we could do that, right? We could do that the brute force method, or you could use your calculator. And so if you use your calculator to do that, you would get what? Temperature final was equal to 29.8 degrees C, right? And so you can either do out the math and do it the long way, or use the solver on your calculator. In either case, you should get 29.8 degrees C. So this is just one example. Another example, right? And you probably think, well, why do we have to know this? Why do we do this? Well, in fact, this equation is used every day around the world, and maybe it's already been automated. They use it so much that they just have a program that they type some numbers into. But in fact, uh, all of the people that brew beer around the world use this equation, right? So the idea is they want to mix some grain at a temperature with some water at a temperature and find out what the final temperature is. So this is actually practical chemistry, and it's used every day. All right, so as a brewer, I don't use a coffee cup calorimeter. Instead, I use a giant 10-gallon plastic cooler. That'll hold the hot water and the grains and keep the heat in. So I weighed out some grain and I crushed it. And then I had to know the starting temperature. So I measured the starting temperature. And when I was satisfied that the temperature had settled down, in this case it settles down at 68 degrees, I heated some water to 164 degrees. I mixed it in, let it settle, measured the temperature. All right, so while we're waiting for that temperature to settle, let's talk a little bit more about some thermodynamics. So remember, we said Q was equal to M times S times delta T. And if we do a quick unit analysis, we know that M is in grams and S is in joules per gram degree C, right? So that means that grams would cancel grams, and we would be left with then that M times S was in joules per degree C. And what that's called is the heat capacity. Now we can use that in the case of if I have two different uh, items combining to give heat to another item. So maybe we had a chunk of iron from our previous example, but maybe we also had some copper as well. So we could include both of those, and we should include both of those for the heat source, the thing that's losing some heat. And that heat capacity is called C. And so we could have the heat capacity times the change in temperature is going to equal the opposite of the mass times the specific heat times the change in temperature. And so in the case where we're adding grain to water, you're probably saying, well, that's only one thing. But in fact, in the lab, we assume that that styrofoam cup doesn't take a lot of heat to warm up. But in reality, the giant 10-gallon cooler that I use actually actually will take some of the heat away from the hot water. Uh, and so we have to take that into account. And we can do that by including it in that capital C value. And so we would have then the C of the cooler plus the C of the grain all times the change in temperature, and that'll be the opposite of the mass of the water times the specific heat of the water times the change in temperature of the water. And so we can include then the effects of the cooler. So what I did is I weighed my cooler, and my cooler, so the mass of the cooler is about 6 pounds. And its specific heat, it's made out of mostly a mixture of high density polyethylene and some polypropylene. And if we look it up, it's got a specific heat of 0.45 British thermal units per pound degree F. Wow, we're getting some strange units here. Now, when I made that beer in the demonstration, the mass of the grain that I used was 6.5 pounds. And if we look up the specific heat of grain, the most accepted value is about 0.38 BTU per pound degree F. Now, you're probably saying, but we're scientists. Aren't we supposed to use the metric system? And yes, I realize that, but I've always brewed beer with English units. And so this is what we have. And so we measured the temperature of the grain, I think was 68 degrees F. And I said the temperature of the water was 164 degrees F. So we need the specific heat of the water, and that's 1 BTU per pound degree F. So now we have all of our units. Now we can calculate that final temperature of the grain. And so let's put in everything we know. All right, so on the left, we have 6 pounds for the cooler and its specific heat, 0.45 BTU per pound degree F. We're going to add that to the 6.5 pounds of grain and its specific heat. So that's the total C. And we'll have the final temperature. And all of that started at about room temperature at the time, which was 68. And so that's going to equal then the heat from the water. So negative mass of the water. Well, I don't weigh out the water. I measure the volume, and I had 2.75 gallons. And if you look up the conversion, you see that it's about 8.34 pounds per gallon of water. And we know the specific heat, 1.0 BTU per pound degree F. We've got the final temperature, and we said the hot water started at 164 degrees. All right, so now all we have to do is solve for T sub F, right? So the units are a little weird looking, but as long as we are consistent with the units that we use, everything works the same. So we could put this into our calculator, and if we put that into the solver in our calculator, we get a final temperature of 146.3 degrees F. So that's what we calculate. So now let's go back and look and see what it finishes at. Okay, not too bad. We calculated 146.3. We measured 146.4. So that's pretty good. So hopefully you learned something. If you did and you liked the video, be sure to hit that like button down below, and we'll see you next time.